This is Donna Nelson at the University of Oklahoma. I'm filming one of my lectures for my organic chemistry class, and in this lecture we're going to cover the first part of Chapter 3 from David Klein's Organic Chemistry text. This is covering acids and bases. And so in this chapter we're going to look at the introduction to Bronsted-Lowry acids and bases, the flow of electron density using curved arrow notation, Bronsted-Lowry acidity, the quantitative perspective, and then the qualitative perspective. So that's the first of the two lectures covering this chapter. So Bronsted-Lowry acids and bases, in that definition, the acids donate a proton, bases accept a proton. You can recall this equation from general chemistry. This acid, HCl, is donating a proton to water, which is the base, and accepts the proton. So this gives you the conjugate base, chloride, and the conjugate acid, hydronium ion. So here the acid is the proton donor, the base is the proton acceptor. We use curved arrows to show the base picking up a proton and the pair of electrons in the hydrogen bond to the acid, moving back onto the atom that bears the proton, so that the base has become protonated and the acid has bears a negative charge. In the past, when we were looking at resonance structures, the arrows that we drew simply helped us keep track of the electron count in the molecule. But here, the electrons are actually moving. So this pair of electrons has to move out a little bit and create an actual bond between the base and the proton. Here, the pair of electrons in the between the proton and the acid donating the proton actually does move in and reside on A. So the curved arrows still pertain to electrons, but they actually do depict electron movement here. This learning to draw mechanisms is essential to any class in organic chemistry. So here is a specific acid-base example. You can see the base, it's a pair of electrons, it's moving in to pick up a proton. The acid is the proton donor. The base is the proton acceptor. Here's the conjugate acid. Here's the conjugate base. The conjugate acid is the base after it accepted a proton. The conjugate base is the molecule, the acid, after it has donated a proton. So here the base is, we say that it attacks the acid of the proton using one of its non-bonding pairs of electrons. The acid, you can think of it as the acid is pushing off its proton onto the base. So here you've got one bond forming, the other bond breaking. Now, quantifying acidity. We quantify acidities. We're going to discuss quantifying acidities and also analyzing acidity by qualifying arguments. So here we're going to look at pKa's to actually quantify the acidity. The Ka values, these are the equilibrium values that describe the equilibrium that exists between the acid and water and the acid that has become deprotonated and the water that has picked up a proton. So the equilibrium values range from 10 to the minus 50th, which is a very slow equilibrium, up to 10 to the 10th, which is also very fast. And so the size of these numbers vary greatly So we use the negative log of the pKa. That focuses on the exponent of the pKa, the pKa value, which ranges from -10 to -50. So this pKa, the pKa ranges from -10 to 50. And so here is what the equilibrium constant describes. Of course, the lower pKa indicates a stronger acid. So the more negative it is, the stronger it will be. This shows some acidity. So here we have sulfuric acid, which you know is an extremely strong acid with a pKa of -9. Here's the conjugate base. So this is the molecule after the proton has departed. This is the acid. This is the conjugate base of that acid. This is the strongest acid. This is the weakest base, because this will not have much of a tendency to pick up a proton and go back to sulfuric acid. That we have many molecules here listed in order of decreasing acidity. So the pKa is increasing all the way up to 18. In this list, we're focusing on this list on organic compounds, and here is T-butanol, tert-butoxy alcohol, tert-butyl alcohol, and you can see that this molecule has a very low acidity. This is the weakest acid on this list. Its pKa is 18, and so this molecule, this is T-butoxide. There's a negative charge here, which on oxygen you may or may not be able to see it. And so you'll need to print off the slides for this PowerPoint talk, which are provided to you. And so this is going to be the strongest base. It will have a very strong tendency to become protonated and revert back to this very, very weak acid. So remember, here are a few of your acids listed. This is in table 3.1 in your textbook, and you can also find a much longer list of acids, pKa's, and conjugate bases listed in order inside the front cover of Klein's textbook. Each pKa unit represents an order of magnitude, in other words, a power of 10. So there's a great difference between these acidities. So sulfuric acid has a pKa of -9. Hydrochloric acid has a pKa of -7. So that means that the sulfuric acid is 100 times more acidic than hydrochloric acid with a pKa of -7. Quantifying basicity. So remember the molecule, the acid that we saw that had the strongest acid, sulfuric acid, it also had the weakest base. And now we're coming down here to other organic molecules. Remember, this is ethane. It has a pKa of 50. So this proton is not acidic at all. Here, the pKa values also, therefore, compare the strengths of bases, because if the conjugate acid, if the acid is very acidic, then that means that the conjugate base is not going to be strong at all. On the other hand, if the molecule is a very weak acid, as in this with a pKa of 50, that means that this base is going to be an extremely strong base and get protonated here and revert back to this ethane, which is a very, very, very weak acid, pKa of 50. So this is an extremely strong base. So the pKa's tell you also about the conjugate bases. Using pKa values to predict equilibria can be done. So here you can see you have this base, which is in with water. And so there is this tendency for the base to pick up a proton and become this alcohol. Its conjugate acid is 18, so that tells you that water is a stronger acid than T-butanol. The base is hydroxide, of course, because the alkoxide has deprotonated water and yielded hydroxide. So that tells you that water is a stronger acid than T-butanol, and that tells you that this equilibrium will go to the right. And you can see that is depicted by this longer arrow in the equilibrium arrows. So the equilibrium favors the weaker acid and the weaker base. So that's another way of telling you that these reactions proceed in a manner that is energetically downhill. So this is the lower energy side of the equilibrium. And so the equilibrium lies to the right. This acid is more reactive than this acid. And so the equilibrium will lie on the right. Using pKa's to analyze the equilibria, more of it, this is a very strong base. You know that because its conjugate acid is a very weak acid. So this is going to be a very strong base. So there will be a very strong tendency to deprotonate water, yielding the conjugate base hydroxide. So acid here, water here is functioning as an acid, giving up a proton, and its conjugate base is hydroxide. This base is picking up the proton from water, and so it becomes protonated. So its conjugate acid is over here. This has, remember, a pKa of 50, which tells you that this is a very weak acid. So note here, this is not even drawn as an equilibrium. This is drawn as a reaction that proceeds to completion. That's because of the great difference between the pKa's. This molecule butane will have almost no tendency to give up a proton, whereas water can give up a proton. It can be deprotonated, yielding hydroxide. Subtracting these pKa values gives you about 34. So there will be 10 to the 34th power more products than reactants. So this is more like just a reaction that is irreversible. You could say that it's an equilibrium that proceeds to completion. Now, qualifying acidity. We've been discussing quantifying acidity, using the numbers, the pKa values, to quantify the strengths. But if you don't know, if one doesn't know the pKa values, you can still compare the stabilities of the conjugate bases. The stronger the acid, the more stable its conjugate base, and the less stable that acid is. When an acid loses a proton, it forms the conjugate base, which now has a lone pair of electrons, which resulted from loss of H+, and the pair of electrons in the bond to the proton moved back onto that molecule. To determine the stability of the conjugate base, you look at the stability of the lone pair, which was just formed when the proton departed. The more effectively the conjugate base can stabilize the negative charge, the lone pair, in other words, the stronger the acid. So an acid, you can view an acid as being very strong if its conjugate base is stable. So if losing H plus leads to a very stable anion, then that acid will be a strong acid. So now we're going to look at the stability, the factors that stabilize the anion, and these are listed in the order of their impact. So the type of atom has the greatest impact, and so you look at the atom that the negative charge is residing on. Is the negative charge residing on oxygen or carbon or nitrogen? And so you look at the type of atom that carries the negative charge. Then you look to see if there's resonance. Can the negative charge be resonance stabilized? Induction, you look at the groups that are attached to or are near to the atom that bears the negative charge. If they are electron withdrawing groups, they will stabilize that anion, and this is through induction. And then the type of orbital in which the pair of electrons resides. So that would be sp3, sp2, sp. And so we will discuss these different factors. They are listed in order here. This is the strongest factor. This is the weakest. But there are some exceptions, as with all rules of thumb, and we're not going to discuss the exceptions. We're just going to focus on you learning and using these factors. These factors that you're learning now in Chapter 3.4, you'll use them again when you start to look at anions behaving in reactions other than just acid-base reactions. So you'll need to know how reactive that anion is towards other atoms, say towards carbon. Here we're only looking at the activity, the reactivity of these anions towards protons. So that will be a different type of reaction when you look at these anions reacting with carbon, but the stability of those anions will still be impacted by these four factors. So we'll look at this, and then we'll cover some chapters in which this isn't really used a lot, but it will be good for you to remember them, because you will use them again. For example, in Chapter 7, Section 6, you will use them. So the first of this ARIO, A-R-I-O, this acronym ARIO, which the A stands for atom that carries the charge. And so the relative stability of the bases tells what the relative strengths of the acids. So you know that a molecule in which carbon has lost a proton, and so now there is a negative charge on that carbon. This is a very strong base because it's very reactive. Oxygen can bear the negative charge more easily because oxygen is higher in electronegativity than carbon is. You can remember the periodic table. And so butane is less acidic than propane. So remember, butane had a very high pH, and propanol did not. So this is more acidic because the oxygen can more easily bear a negative charge. Then the second letter of the word REO. R is for resonance. Compare the stability of these conjugate bases. So this is propanol, which has lost a proton. This gives you, ethanol, which has lost a proton. That gives you ethoxide. So this negative charge is residing completely on oxygen. And over here, this would be the conjugate base of acetic acid. And so this is the molecule acetic acid after it has lost a proton. And notice that negative charge can be spread out across the two oxygens. And so this is, the negative charge is delocalized. This, with the resonance structures, is going to be more stable. Remember, generally, the more resonance structures an anion has, the more stable it is. So this has two resonance structures, that has only the one individual structure. And so by just using the reasoning that you already have, you have been able to determine that this anion is going to be, or is, more stable, and that you did that without looking up any pKa's. And that will be the situation that you're in generally. And so this, you'll need to just know these factors so that you will know this and not have to constantly sit and look up pKa values on a table. Here, this is REO. You can see the I is for induction. The induction can stabilize a negative charge by spreading it out. Anything that one does to spread out a negative charge or a positive charge or unpaired electron density in a radical stabilizes that reactive intermediate. So carbocations, carbanions, radicals are all reactive intermediates, and all of those are stabilized by spreading out the charge or the unpaired electron density. So here we're looking at stabilizing the negative charge that is formed when a proton is lost, because we're looking at acidities. So here are the pKa's of these molecules, these acids. So this is acetic acid, this is chloroacetic acid, dichloroacetic acid, trichloroacetic acid. So you can see the trend here is to gradually add chloro substituents. 1, 2, 3. And as the chloro substituent is added, the pKa decreases each time. And so that tells you that these molecules are gradually becoming more acidic. And that is because the pair of electrons that is in the oxygen-hydrogen bond is being pulled back onto the molecule. Here, the pair of electrons that resides on oxygen is being stabilized by the negative charge being spread out. Here, the chlorine is going to be partially negatively charged. Both of these will be partially negatively charged. And now all three of these will be. And so, as that electron density is being pulled back, the proton here becomes more and more bare of electron density. And so you can think of it as the proton, the electron density, which is holding the proton onto oxygen, is diminishing. Or you can think of it as in the anion, the negative charge on the oxygen is being stabilized by the electron withdrawal. Now, the type of orbital also affects the stability of the negative charge. The closer the electrons are held to the nucleus, the more stable they are. So the shorter, and also the shorter the atomic orbital is, if it's close to the nucleus, you can approximate how close the orbital is lying to the nucleus by looking at the S character. How much S character? Well, this is sp hybridized, so it's 50% S character. And notice how in the drawing, the orbital is shown lying closer to the nucleus. Think of the S orbital. The S orbital is just simply round, and it's lying very close to the nucleus. The nucleus is embedded in the middle of the S orbital. So here this is 50% S. Now this is 1/3 S, and this is 1/4 S, sp3. It's 1 part S out of the 4 parts. So this is 25% S. And so here a bond that is formed using this orbital will be longer. You can see here because the sp3 hybridized orbital is the longest. This is shorter. This is the shortest. And this, the electrons in this orbital are going to lie closer in to the nucleus. And when they lie closer into the nucleus, they're going to be more tightly held and more stable. And so you have to consider the type of orbital that the unpaired electrons is residing in. The unpaired electrons that is giving rise to the negative charge. So let's look at this. Here we have a proton that is attached to a carbon, which is sp2 hybridized, and a proton that is attached to a carbon, which is sp hybridized. So this carbon is bearing the orbital that is sp hybridized. The pair of electrons are in the sp hybridized orbital, and that's where they will stay once the proton is lost. This pair of electrons is in an sp2 hybridized orbital, and that's where they will reside once this proton is lost. And so thinking back on, and you could look back at the orbitals that we just saw on the previous slide, because these electrons are not so close in to the nucleus as they are here, this one is going to be more stable. This anion with the sp hybridized orbital is going to be more stable than this ion with its pair of electrons in the sp2 hybridized orbital. And so if you look at this molecule, it contains both a carbon-carbon double bond and a carbon-carbon triple bond. This end of the molecule will be more acidic. This functional group, the alkyne functional group, will be more acidic. And indeed, later on, we learn that alkynes are considered very acidic organic molecules, and this is exactly why. When assessing the acidity of protons, we generally use REO as the order of importance of these stabilizing effects. So here, this is the most important, next, and least important in these four criteria. And there are exceptions which we're not going to get into because I think it's much more important for you to, learn the rule and be able to apply it than worry about the exceptions right now. I think that will just become confusing. So ethanol is more acidic than propylene. Once this proton is lost, the pair of electrons will reside on oxygen. So look at this. Once this proton is lost, the pair of electrons will reside on carbon. However, this is resonance stabilized. So you have to decide which has the greater effect, the pair of electrons residing on oxygen or the pair of electrons being resonance stabilized. And you can see from the pKa values that ethanol is more acidic than propylene, and so that means this anion is more stable than this resonance stable anion, because this anion, the negative charge, is residing on oxygen. And so that shows you how this is consistent with the order of priority in REO. And you will use this again in 7.6. So it's good to learn it now and don't forget it. So this finishes the first lecture for Chapter 3, Acids and Bases.